Hi YouTubers, this is Brett Zook here with Zook Mechanical, or Zook Mech, my YouTube channel. I just wanted to give an update on my reaction torque dyno. Made some good progress on it. We've got the mounting box put together. It's not glued up. Still got to get some fans and some pass-throughs to get the electric out. We've got a motor mounted on it, coupled, and it's currently functioning. So I just wanted to give you a little walkthrough. I haven't done a video on this yet. I've been working on this for about 2.5 years, so we'll just go through a little walkthrough and kind of talk about how it works and what I'm trying to do. So a couple years ago I got into RC oval racing, and I've got two oval pan cars, a 17.5 car and a 21.5 truck. That's the number of turns on the motor, and I wanted to build a rig to be able to test motors on and determine what timing I should be running and where their peak power and peak electrical efficiency was, and also be able to look at the same manufacturer's motor but just different samples of the same motor and see how much variance there was. So that's kind of what got me started down this journey. So this is the dyno. This is a reaction torque dyno as opposed to an inertia dyno. The way this works is there's a 17.5 motor in it right now. That's from the old Xfinity class. I just had one laying around, and it's coupled to a brushless outrunner. That's what the gold motor is that's being turned, and you can notice that the outside of the outrunner motor is turning, but the back plate is stationary, and that back plate is mounted to a trunnion, which is this guy right here. So that's just basically like an axle. And what's going to happen is there'll be a torque arm that's going to mount to this hub, and that torque arm is going to come out to about here, and then it's going to push down on this guy right here, and that's a strain gauge. It's basically a scale, and so that's going to measure force, and if I know force at a distance, then that's going to be my torque, so my mechanical torque. I like the reaction torque dyno better than an inertia dyno because I can hold the motor at different speeds under different load conditions. You don't just get a single pull. You can actually hold the motor there, so if you want to heat soak it or if you want to do run after run. That's the main part of the dyno. I've got a just stock zero timing speed control. My plan right now is just to adjust the end bell timing to get these curves. So that's what's powering the motor. And then I'm running the output power. We're actually loading the gold motor, the brushless outrunner, that we're using that as a generator. And eventually the three-phase wires, red, black, and yellow that you see there, they'll pass through the bottom of my motor plate here. I need to mill this slot out a little bit bigger because you don't want those touching anything, because that'll mess up the force reading if that happens. This is a solid state relay, this guy right here, and I'm controlling that to control the load. So the way this works is the brushless outrunner is making AC power, and I'm running it through the black three-phase rectifier right here. And so you can see right now we're making about half a volt, 4.45 volts there. That's DC. That's coming out of the three-phase rectifier, and then I'm PWMing that signal into a little load bank for my iCharger 406 right there. So that's a quarter ohm. Basically, that's a quarter ohm resistor, and so I can vary the load on our generator by how much duty cycle I drive into this. So both the just stock speed control and that SSR that controls the load are being controlled by an Arduino. So that's got some code on it that is reading some sensors, and then also reading those two potentiometers I have on that white breadboard there. the sensors that I currently have hooked up. So I don't have the force meter yet, but I do have this watt transducer. This is an autopilot watt transducer. This basically does what a Sam's Rev meter does, for those in the RC car world. And we're running power out of this 5-volt mean well power supply. This is a 70 amp unit, and I've got it turned down so under load it pulls just under 4.22 volts, which is where we charge our batteries typically. We've got the Hall effects out of the motor are broken out. You can see where I split the Hall effect cable from the motor. That's this one right here. And so I've got it split in the breadboard, and I'm taking phase A Hall effect signal and I'm running it over here too, so I'm using that to calculate speed. And then I've done quite a bit of work, so you know, doing the machine work. I did that at a family member's machine shop that I used to work at a long time ago, but I still had access to it. Watched a bunch of woodworking videos and then decided I would make some dovetails in my little wooden box there, so that was a little bit of fun. And the other thing that I've been doing, so I haven't been able to race this year. Our local track closed, so I've been working on this thing in my spare time. The other thing I've been working on quite a bit is learning Python, and I'm using a program called PyQt, and that's used to make user interfaces. And so far, quite a bit of learning to get that all going. But I just this weekend got the Dyno to talk to the computer, so this is the way that I'm going to be able to interface with the Dyno, and this is how I'm going to record my polls eventually. So right now we're looking at a test data screen, so this is just kind of a status screen. We've got current. Now that's current that's coming from that power supply into the speed control, and voltage into the speed control. I've got a desired speed, so that's where I want the motor to be running, and I have the throttle turned down right now so it's not going very fast. There's the actual speed here, and we're going about 450 RPMs. Electrical power, that's just the current times the voltage right now, so that's our electrical power in watts. This right now is brake load, so that is the duty cycle that I'm sending to the SSR to put load on the engine, so right now there's no load. Eventually I'll make this brake mechanical power, so this will be the speed of the motor times the torque calculation that I do with my force meter, the scale that we looked at. Then if we take that mechanical power and we divide it by the electrical power, we'll be able to calculate an efficiency. So that kind of tells us how much heat got wasted through the speed control and also through the motor and any of the wiring in the power package. So that'll just kind of give us how much, you know, energy is lost from the battery just going into heat. And then eventually, when I figure out how to calculate it, I want to get a timing, so this would be similar to the timing from the modalizer, and I'll probably just do one phase. I may do more phases later. I'm also going to add a motor temp. So if we're doing a test right now in my setup screen, we'll be able to set that to a temperature that will stop the test. Otherwise, we'll just keep the data to see how hot the motor was running, and then throttle percent right now. So I've got about 18% throttle on it. So that's all reading. That was quite a bit of work. This is still a work in progress. This is the first screen, so we'd be able to put in what the motor manufacturer was, number of turns, what we're doing with it, and who owned it. And this is the test setup. So I've got a min speed, a speed step, and a max speed, and a speed variance. And so the idea is when you started the test, it'll try to go to this max speed if it can, and it'll take some number of samples. I haven't decided yet. It'll take some number of samples, maybe 100 samples, while it's at that speed. Then it'll step down to the next lower speed by this increment. So our next increment down will be like 11,500. And it'll take another 100 samples and it'll average these together, and it'll until it gets down to its min speed, and then the test will be over. And so we'll get a nice steady state curve at each of those speeds. And here's a speed variance, so trying to hold the speed within 100 RPMs or something that's settable. Motor timing, and then this would be the kick out temp. So if the motor temp got hotter than that, we would abort the test automatically. This is not completely done yet. Still got to work on getting it automated. Eventually, the whole dyno will be controlled from this GUI, but we don't have that done yet. I've just this weekend got it reading. So, and then we'll have a data plotter tab where we'll be able to plot the different curves that we've done at different timings. And then I've got a calibration, so this will be a screen. It's not finished yet. That'll be how you set up your ESC for your power package, basically how you calibrate the throttle. And then we'll also need a calibration for that scale. So this is a work in progress, not finished yet. We'll go back to the test data. And a couple of things I've learned in this project. If we go back over to the dyno, I've tried a couple of different outrunners, and I chose this one because it had 60 amp running current, and I thought I would really need that type of wattage so that I didn't burn the load motor up. So basically it didn't burn up the generator. But what I found is for this size of motor, 17.5 motor, this motor has quite a bit of parasitic on it, and it doesn't allow me to get up to the top end speed range of this type of motor. Should be able to get a lot closer to 10,000 with this Xfinity motor here, 10,000 RPMs. So I think this would be a good motor for 2-cell racing. We could probably get quite a bit closer to the actual speed, but it has a lot of parasitics just to turn it. So I'm going to turn the dyno up in a little bit and show you that it draws about 9 amps at about 8,300. So I think that what we're going to do eventually is move to this smaller motor. This is a 800 kV motor, 890 I guess, and that the gold motor is an 800, so this will do pretty good. It'll make about 10.5 volts at close to 10,000 RPMs, and I think this will be fine. It's got about a 30 amp running capacity, so it should be okay, and the tests aren't going to be that long, so I don't think it'll get that hot. So that's what we may end up switching to. The other issue is this coupling that I've used. That's a spring coupling that's laser cut, and it seems like it gets wound up torsionally and causes a resonance at about 7,000 RPM. So I need to probably replace that with I'll probably replace that with a Lovejoy that's got a spider in the middle of it, just so it seems like it's at 7,000 it gets into a resonance, and it seems like it's shoving the drive shaft of the motor back and forth, which we don't want because it could start slamming the rotor into the Hall effect board, which could damage the board, so we don't want that. So I'm going to have to change this coupling eventually. You'll see what I mean when we do a pull on here. And again, I don't have it automated, so I'm going to be running it with these two potentiometers. And then we'll watch the readings here on my output here. So we're going to turn it up, and it's going to get a little bit loud, and I'll try to talk over it. So we're going to turn it up. Okay, so we're at basically 100% throttle. You can see that we're drawing 9 amps, and we don't have any load on it. We've pulled the power supply down to 4.2 basically, bouncing around, and we've we've achieved about 8,350 RPM, say, and we're pulling 38 watts. And that's just with no load on the unit. And